All right, hello everyone. Welcome to Pop and Push. You're probably used to seeing Shafu here, but this time I'm hosting an episode on his behalf. Here today we have actually I should probably introduce myself. I'm philogy. You might know me from the Twitter circles doing smart contract stuff. And today with us we have Moody, the core dev slash founder of Ekubo, a new AMM that's rapidly gaining traction in the DeFi space. And yeah, today we're going to talk about some like really technical nitty-gritty details of like smart contract implementation. Um, yeah, Moody has made some big claims and backed them up on Twitter in terms of efficiency and being like the most efficient EVM AMM out there. So yeah, super excited to learn how that was achieved, how you think about smart contract development in general, and also dive into other details you don't mind sharing.
Yeah, sounds great. Thanks for having me. Um, let's get started.
Yeah, why don't we dive straight in? Maybe you want to give some background, like Ekubo, like why you started developing it and what were your thoughts behind it?
Yeah, so actually I started Ekubo as a bet on Starknet in particular. So we started on Starknet. We launched in 2023 and we developed there for exclusively for about 2 years in the Cairo contract language. One cool thing about Starknet is you can upgrade your contracts pretty trivially, and there's no real overhead because they separate the code declaration from the actual smart contract deployment. So there's sort of like built-in upgradability on Starknet. So we had a lot of opportunity to iterate on Starknet in the design, efficiency, how things worked there. Um, and we took that design and we ported it to EVM recently, and we're now going multi-chain. So for about a year, we were only on Ethereum with this EVM version, primarily because our biggest advantage is how efficient our smart contracts are. But now, we have these contracts which work really well and have features that aren't available anywhere else for EVM. And so now we're deploying it cross-chain, multi-chain. Um, and yeah, we've also sort of recently changed the model from, this is a smart contract that earns revenue for the Ekubo DAO uh, via a withdrawal fee. We've changed the model now, and it's fully open source and permissionless. And our core contracts actually don't even have an owner, a concept of an owner or revenue. Um, so yeah, that's the focus of this latest version, as well as many gas efficiency improvements as we could fit in. And it turns out, even though V2 is very efficient, we could fit in quite a lot into V3. So yeah, happy to share some of those tricks.
Yeah, one thing real quick that I was curious about. So you mentioned that the newest Ekubo version V3 is open source, but also there's like a special license on it. Like, um, how is that?
Yeah, I guess that might be a little contentious if me saying open source, but so as long as you don't charge any protocol fee, you can fork these contracts, deploy them, build on top of them completely for free. So that's kind of what I mean by open source. It is a proprietary license. If you do charge a protocol fee, you have to share 50% of that protocol fee with the Ekubo DAO. And that's kind of like the default. You can negotiate different terms with the DAO if you like. The DAO is sort of the licensor. It controls the license text via ownership of an ENS name. So it can add exclusions, or uh, or grant the license to um, specific use cases, um, or negotiate the revenue share. Um, and yeah, so you can kind of think of the DAO as like the licensor of the Ekubo smart contracts.
Oh, interesting. So unlike other contracts that are typically like completely proprietary until like 4 years or something, like the classic business license that Uniswap or Avi use, it's more like it's open source directly, but with like limitations on quote unquote commercial use when it comes to revenue. That's pretty cool. Also, before we dive into the detail, one last thing. You mentioned before, do you work alone on these smart contracts, or do you have a team? How does Equitable as a whole operate? Is it more like a solo indie dev type deal, or
Um, yeah, so uh, I work with a couple of people. One person is a full time employee. Actually, a few people. Um, we're all sort of in different roles. Ekubo has one full time employee. He's a front end engineer, so he works on things like everything that uh, comes after the contract. So indexer, API, interface, all that stuff. He touches above the contracts, and then on the contracts themselves, it's mostly me. I do, in this latest version, I've made extensive use of AI, so like I feel like that really multiplies the force a lot. Uh, and then we have a contributor. Uh, his his pseudonym is D. Herdplatt, uh, and he helps a lot. So he's read the contracts, he's made contributions, but primarily for the contracts, it's been me writing the code.
Interesting. Okay. Yeah. So let's finally get into the technical side. And yeah, should we dive right into core, or do you want to show off the hook system first? What do you think?
I think maybe we start with uh just sort of the core contracts. Like maybe it's best to like go through the interfaces,
Hmm.
because that kind of gives you a better overview, and then we can dive into like the tricks that we've done, um, that make things much faster. Um, but yeah, I think it's best to give like an overview of like how the contracts are structured, starting with the core contract. Um, so um, Actually, even before the core contract, there's something called the Flash accountant, which is more like it's a more generic concept that it would be helpful to be familiar with. Um, so basically, the core contract is built on top of this idea of a Flash accountant. Um, a Flash accountant is just a contract where you can acquire a lock. Uh, you can you can call functions on that contract within your callback, which might accrue debt, or the contract might owe you some money. So there's a concept of a debt which can be negative. In the case that it's negative, the contract owes you money. Um, and by the end of the lock, by the time you return from your callback, you have to make sure that you've zeroed all your debts. Um, and so this concept of flash accounting, like it's the most trivial use case would just be a flash loan. So you can lock the contract, you get the callback, you can take those tokens out, do whatever you like with them, and as long as you pay them back, uh, then then when you return from your function, the contract won't revert. Um, if you don't pay it back, then it would revert with this debt's not zeroed error. Um,
So this is very similar to Uniswap v4's system as well, right? In
yes,
terms
it's
of keeping track of things transiently and then having these like callbacks you can only interact with from within like a locked context.
yep, that's right. But it's separate from the core contract, because it easily can be. So it's sort of like this base contract, which which you could use in any system. You could just use this repo as a dependency and inherit from this Flash accountant, uh, and take advantage of these like internal functions uh, that let you manage the user's debt with these different operations. So it's a very efficient implementation of what I usually call the till pattern, where you like open the till, you can take money out, put money in, as long as you haven't changed the the balance of the till, like you can close the till.
That's a cool name for it, actually. I haven't heard it called like that before. Tilt pattern.
Yeah, I actually gave a talk about this. So previously I was the eng lead on the V4 smart contracts, and so this is a pattern that I came up with for Uniswap V4. Um, and yeah, it's a very good pattern, especially when you have users who want to interact with many different, uh, I guess you could call them pools, or like you could call them money markets or lending or whatever. When they want to touch um, many different vaults or whatever you want to call it, uh, stateful reserves. I don't know. Uh, when a user wants to touch many of those within a single transaction or single operation, like a trade, this makes things much more efficient because you don't have to actually interact with the token contracts at all. So yeah, this is gonna, I think, basically be the standard for any future, you know, DeFi type protocols, because that's a very common thing you need to do. Um, but yeah, in our case, we've done a lot to make it, as efficient as possible. We even optimize our usage of transient storage, so we only store things in a single slot. Uh, and in many cases, we even store things like the current locker in a single word in memory. Um, and so yeah, that's a very common thing you'll see in these smart contracts, is that we created a lot of custom types just to limit our usage of call data, of stack. So like, sorry, yeah, when I said in memory, I meant this locker thing, which is that it's actually stored on the stack, and it only takes one word, so that reduces our even our stack pressure for Solidity. Um, yeah.
Do you feel like that would have been necessary if Solidity was like better at stack scheduling and like manipulating things on the stack? Like, would you be more inclined? Would you have been more inclined to use like more separate variables and not continuously pack and unpack things, or do you think that the packing and unpacking at the end of the day actually like net saved you, irrespective of like Solidity's inefficiencies?
Yeah, I'm not sure that you can actually build a compiler that like does a better job than we do here, because there's cases where, uh, yes, you want to pack things into storage or transient storage, so custom types are great for that. But there's also cases where you want to read it, but you only want to read, you know, uh, the 20 bytes that represent the locker, and not the locker identifier. Um, and so yeah, I think there's like two places. I think maybe the compiler could do a better job of like knowing, hey, you only care about these 20 bytes, and not parsing things out if you have like a struct, for example. Um, but uh, but yeah, there's also like cases where you're passing it around to other contracts, and those might not have. Uh, yeah, you're passing around to other contracts, and you want to keep it just in a single word, because that reduces like your ABI decoding and encoding overhead, and also the length of your call data, and which means less memory usage. Um,
Makes sense. So the packing is not only about manipulating it on the stack; it's actually also a lot about passing it around, like serializing, deserializing it via ABI, and also specifically like transient storage and normal persistent storage.
yeah, yeah. I think maybe the compiler could help in some of those cases, but I think having this custom type, you have a lot more control over it, and so you don't really need to worry about it.
Hmm.
Because when your locker is a bytes 32, uh, it's always going to take a word, and that's the most efficient representation of it. Um, so yeah, it
The
just makes
reason I
things a
asked
little
that is
easier.
because I kind of misunderstood initially. I thought like part of the packing was also just like for pure manipulation, like on the stack, like within a single like EVM call, like within a function. But yeah,
There
makes
are
sense.
cases where it helps with that. Yeah. Um, yeah. So yeah, I mean, we make extensive use of those types. Like, we have many different types.
Hmm.
Most of them actually fit in a single word. Um, so like something like the buyback state, we have a lot of different um, things that are stored in this, but at the end, they all actually fit in a single word. Um,
Hmm.
So like it's nice if like you only care about, the last end time for a particular EVM call. That's the only thing you actually parse out of the word. Um, so yeah, that's the Flash accountant. I think maybe we can look at the core interface now. Um, well, maybe it would be helpful just to go through this interface. It looks like we're not getting syntax highlighting for some reason. Oh, there it goes. Um,
That's Flash Accountant.
yes. Oh, another thing we do a lot is, okay, so you enter this function via the lock function, via the lock call. And so you'll notice this has no arguments. So like when it makes the callback, how do you know what to do, or like why you actually lock the thing? Because
Yeah, like where's
and
the callback
so
data?
yeah, so actually one thing we did at a lot of places, because Solidity is not very efficient with like byte array ABI encoding and decoding. We actually just encode the callback data after the function signature. So you can see here any data passed after the function signature is passed through back to the caller. So this ends up saving more gas than you would expect. This is something we do in a lot of places. So it's kind of just like custom ABI encoding and decoding. Turns out there's just like a lot of overhead related to it, especially when you're dealing with like types that don't take up the whole word. You can sometimes pack them and say call data, and yeah, also save on validation, because let's say it only takes 20 bytes. When you pack things, you can just load the right amount and then shift it right, and now you have all zeros in the 20 bytes and the other 12 bytes. So it saves you on validation. You have to do any validation of the input if you only accept 20 bytes. So yeah, we do that in a lot of places. So lock, for example, forward, start payments, complete payments, withdraw. We do custom call data, update that. Even this is actually a security feature. The fact that it has to be this very specific encoding means that you can't do it by accident. That's one of the reasons we did that here. And yeah, I think we make extensive usage of that throughout the contracts. Another little trick we did with the Flash accountant is this selector. We mine this function selector so it's 0. So when you get the locked callback, if the first 4 bytes are 0, you can go straight into your callback logic.
Oh, nice.
And so like a lot of these things, these ideas, we have like extensive gas testing in our unit tests. So like a lot of these ideas, we first tested to make sure that they did save gas and the amount of gas was appreciable. So I think there's I just want to create like an appreciation of like how much time it actually takes to get these optimizations, because you can't just tell Claude like optimize this contract. You have to like optimize it, run the tests, make sure your gas costs increase, make sure it's actually worth whatever like developer experience cost you have. Like maybe you can make some abstractions over it. But yeah, like even just like having those ideas and testing them, like it takes a lot of time of an iteration just to figure out where are these contracts spending the most gas, where can I shave off the most gas, and those ideas become more and more minuscule. But like that's what it takes to make these contracts so efficient, because we're on the frontier. We have to make these little micro optimizations everywhere to get like an appreciable difference.
Yeah, so let's dive into core. Like the till pattern is super cool. Also, when I first read V4, I thought it was super cool, and also seeing it here, like pushed even further with the call data encoding. And what about core? So you also have like a tick based, range based AMM, right? Where with concentrated liquidity, but you represent the positions in liquidity different, right, than Uniswap before. And you also have like a dual. I read the contracts a little bit, and you have like a dual stable swap and like concentrated swap mode, right?
Yeah, so we have like a special representation for stable swap pools, um, which shaves a lot of gas off. Basically, because of Uniswap v2's simplicity with full range pools, it can be cheaper than concentrated liquidity in Uniswap v3. So there are cases where you want to have full range pools just for gas efficiency. But the more important thing about these full range pools is they simplify a lot of things you want to do with extensions. Um, so primarily the way we use full range pools is to simplify our extensions on top. Um, so uh, so yeah, without going straight into extensions, even though these are kind of like a big part of core, um, maybe I can start just with the core interface. So you can see that
Mm-hmm.
core is Flash Accountant. It's also exposed storage. Basically, exposed storage just lets you do arbitrary storage reads from the core contract, uh, which means that we don't have to have any getter functions on the core contract, um, because we can just have libraries which let you fetch whatever data you want from the core contract. And they also let you do it more efficiently uh, because you can fetch many different storage slots in a single call versus getters. Each get would be a separate call, which would just add unnecessary overhead. Um,
To fetch multiple, is it just like you pass in a list of slots and it reads those out, or is it more like a delegate call, situation where you can like read out whatever you want in the callback contract? Okay, it's a list of slots.
yep, we use the same trick where you list the slots right after the function selector instead of having some array of bytes 32, which would add a bunch of Solidity overhead from the Solidity compiler, just for ABI decoding and encoding. And so, yeah, we do a direct return here in the assembly of the results. Um, and so, this has a developer experience overhead, but of course, we can write libraries which tell you how to get, each of these storage slots. And in some cases, we even load multiple slots in a single call, which makes things more efficient. Um, yeah.
Yeah, I think this actually sets a cool precedent because, as a fellow optimizer myself, I also sometimes get annoyed about how inefficient certain things in, the Solidity ABI are, but like the EVM and Solidity itself as a language is flexible enough for you to do a lot of non ABI things. And maybe this is also a signal that actually, as a community, we should like create a new standard for these kind of things. But a lot of the things you show here seem like relatively straightforward to integrate with. Like if you either have like some assembly know-how or if you provide good, libraries on your end on the Solidity side. But I imagine like in the front end it could pose some challenges. Or how have you found that in the integration process?
Well, for the front end, we wrote these data fetchers, which sort of abstract away all the things you would care about, and they're purpose built. So, the quote data fetcher, for example, is for aggregators who want to be able to quote against the pool off chain. You need to know what is the current price of the pool, the current liquidity, and also all the ticks around the current tick. Um, and so we built this, which provides a very useful representation of all that data, and it abstracts away, fetching. So we do all the necessary function calls and parsing and all that stuff for you, so you don't have to worry about it. Um, but yeah, I think it's pretty easy uh, to abstract it all away with libraries or lens contracts for whatever use case you need. Um, yeah. So maybe we can dive into the core contract a bit more if we don't get distracted with another another side.
Yeah, there's so many like interesting like small goodies in here, but yeah,
Yeah.
please continue.
So okay, so here are the events. We have this pool initialize event, which associates a pool ID with a pool key. Um, the pool ID is just the hash of the pool key, but because you need to be able to map the two together, um, we always emit this event with the actual pool key, the pre-image of the hash. And then everything else is just associated with the pool ID, which is just a 32 bytes word, just a hash of the pool key. That saves a little bit of call data. Um, and yeah, the events are basically one-to-one with the functions that you can do. So you can update a position, you can collect fees on your position, you can accumulate fees to a pool, which just basically means you donate them to the pool. Um, we have some errors listed here, not that interesting to go through.
One thing I'm curious about, considering how gas conscious you are in this contract, why do you have events? Or maybe, I guess you don't have a swap event, but you kept events for the others? Or how's your thinking around events and whether to have them or not? Because I remember V4 also, while they were in the development process and while I was still at Sorella, like we did go back and forth a little bit on whether V4 should have events. I'm wondering how you think about that.
Yeah, so it's just really hard to build an indexer around a contract if you don't have events. And we don't really want people to be tied to like proprietary tooling, just to like be able to keep track of what happened on a smart contract. Um, so yeah, we have events basically to support our own indexer and our own use cases. The thing is, we do have a swap event, in fact, but it doesn't have a signature because
Mhm.
we have no topics on the swap event, and that's another gas savings. Um, the we just emit a zero topic event, and we know if there's no topics on the event from the core contract, we know it's a swap event.
Oh,
Um,
interesting. Okay. That's
yeah,
a cool
just
way to
another
do it,
gas
actually.
optimization. Yeah. And we use that in a few places where things happen on every swap. We don't want to waste gas on a topic because we know it's a swap event. Why would we emit a topic? Um, so uh, so yeah, I mean it's definitely it's like definitely a question like events cost you 1,000 gas per swap, but like it's too useful for everyone who integrates to get rid of. Um, Everyone wants that event, for their infrastructure. So I think that's a case where the DX cost is just way too high. Um, yeah, and it's also possible in the future that the cost could be reduced if they, for example, remove the bloom filter from the block header. Um, I don't think that would really affect people's use cases, but it could reduce the cost of events significantly, and it wouldn't require any changes to the contracts. Um, Whereas if we did exclude events, we might want to add them back later if they reduce the cost of them.
Interesting. Yeah, that makes sense.
Yeah. So so yeah, the um from there, yeah, so I mean the life cycle of a pool is first you initialize it, that emits the pool initialize event. Um yeah, so actually I mentioned that we don't have getters on the core contract, but in this case we do have two getters. Um and this is sort of an exception. So there's a particular case where you want to uh where exposed storage isn't the most optimal way to do things, and that's when you are conditionally fetching things from storage. So maybe you want to fetch one storage slot, or maybe you want to fetch 10 storage slots, but that depends on the current state of the pool. Um, and so that's why these functions exist on the core contract, is because it can potentially fetch 100 or 1,000 storage slots, but we don't really know how many it actually needs. So There's a few cases like this where we have getters, but I think this is probably the biggest one. Um, yeah. So and then one thing that okay, so this function is pretty important for extensions. This update save balances. Uh, so with the Flash accountant, you never have to actually transfer tokens. Uh, when you do like multiple operations, like multiple swaps or position updates. But let's say at the end of this transaction, you have a non-zero delta, but you don't want to transfer the tokens out of the contract because you're gonna just use them later, which is happens a ton with extensions. Um, this update saved balances lets you uh, change. It lets you store, like permanently store in the core contract the amounts that you're owed while updating your deltas or your debts, so that you can come back and use them later. Um, I don't know if I explained that well, but
Yeah, it's similar to. I keep drawing parallels on V4, which I mean makes sense since you worked on that too. But yeah, it's like V4 is like stored deltas, right? You can mix. You can on V4 you can mint a 6909 token to store your deltas, and then you can burn them again to basically it's like a I don't know, it's like a coupon or like a UTXO. You can just
yep,
mint it and burn it with a lower overhead.
yeah. We didn't bother with the complexity of like 6909 because it basically isn't worth it. Also, you can build a 6909 which uses this thing externally. Uh, one thing to note is that we have both token 0 and token 1 here. That's because you can store two, token total supplies usually aren't more than UN 128 bits. So you can store two
Hmm.
balances at the same time, and that this lets you save storage when you do that, which is very important for extensions, which usually operate on a particular pool. Um, this this saves you a lot of gas because you don't have to do two save calls because you're usually dealing with two tokens, basically. Um,
Interesting.
is another case of a getter where it's it's more efficient if we know the pool state, so we just have a getter for that. Um, and
So do you do anything different in the like main swap loop or like ticks representation? And also maybe a general high level question. Since you worked on V4 and also this, how come you got this to be so much more efficient than V4? Is there like different set of trade-offs that you had to take while working on Uniswap versus here? Or like what is your like how did your approach change and what let you make like these larger gains when working on this version?
so when I wrote all the contracts for Starknet, um, that I I spent a couple years optimizing them and working on them, uh, and like building out features. Like for example, TWAM is not something I worked on uh, basically at a production level at Uniswap, and I didn't even really work on the code at Uniswap. Um, so there's like an example Uniswap before TWAM extension or hook, but it's very different from ours. Uh, so I I think it's just the experience, the amount of time that I've been iterating on this design. So even for EVM, we had a V1, and then we had a V2, which introduced some major optimizations, and then we had a V3, which is even more efficient, and that's where a lot of these like extreme micro optimizations came from. So I think like um, our V3 is 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 more efficient just like from the sum of like many small optimizations, and in many cases I was surprised by how much gas like Solidity was wasting in certain things. So uh so yeah, it's just the amount of time, like I guess like sharpening the blade or whatever. It's like so much more time has been invested on these contracts than uh, probably even like Uniswap before, just with optimizations in particular. And then we have differences in design that came from my experience building things on Starknet. Like uh, like one of the main things that uh, I think was sort of like a breakthrough for Ekubo is this function in the Flash accountant called forward. So we use this extensively in our Ekubo extensions, but it just doesn't even exist in V4. Uh, and even though it's like such a simple idea, it allows these extensions to operate much more like they're a part of the core contract. Um, and so the idea is that you've called lock and you want to interact with some extension or whatever, maybe it's even like a router that has some additional code and logic. Um, you can just forward access to your lock to a different address. Um, and then that other address can do whatever it likes, and then you're going to be responsible for zeroing out the debts at the end. Um, and so this allows extensions to operate within the Flash accountant of the core contract, if that makes sense. So you don't ever transfer tokens to extensions. Um, there's not like any additional token transfers or approvals or anything when you're working with an extension. They work a lot just like the core contract. Um,
I see. So basically, it's like when you call lock normally, like in V4 here, it's like you establish the sender, like the contract, like probably the router, as the person who's allowed to like interact with the till and do things. But then if you want an extension on top of that to also interact with the till and do things, you can't directly do that in V4. But here with forward, you could call another contract, like the router, for example, could call like an extension contract, and the extension contract could do like a bunch of things on behalf of the router. Am I understanding that correctly?
yeah, exactly. Um, yeah, it allows for like a lot of uh, use cases. Like for example, let's say you want to build like uh, a permissioned pool. Uh, you might want to pass additional logic or additional data with your swap call to the extension, right? Uh, so it's not obvious how you would do that with like V4, but it's pretty obvious with this forward thing. You can just prevent anyone else from swapping against the pool using the before swap extension, before swap call point, um, and then force all swaps to happen via forward. And then you can take whatever data you like. You can charge additional fees. You can return whatever data you like, um, and
Isn't this
it just
similar
works.
to what Uniswap has with hook data?
Uh, Maybe, but I'm not really familiar with that, to be honest. So my time at Uniswap ended, when I started working on Ekubo. So I wasn't really following V4 development after that. And there's there's probably a lot of changes that they made to V4 that I personally wouldn't
Yeah,
have
I'm just
agreed
trying
with.
to also draw an analogy for myself and for the audience. So basically, in Uniswap before, you can record hooks, and hooks can inform the main pool manager about their capabilities via like bits in the address. And basically, the hook data is just like a field that you add to like any modify liquidity call or swap call or initialize. I don't think it's not present on initialize, and that's just like data that gets verbatim forwarded to the hook, and it can be anything. Like the hook can do anything on that. It can be signatures, it can be extra instructions. So I'm just
Yeah,
wondering if the functionality
yeah,
it enables it's kind of like the parallel here.
right. But this is more powerful because you're not limited to the operations that are defined in the core contract, right? So you're not limited to modifying positions or swaps, which is extremely important for things like TWAM, where you might want to create a long-term order, right? Or a DCA order. Um, and in that case, you're not doing a swap or a position update. You're doing something totally different, right? You're creating an order. Um, so uh, so I can show you, for example, in extensions, um, we have multiple different examples, here's TWAM. Uh, when you want to create an order, what you do is you call forward to the TOM extension with a particular call type, and we handle your call data a different way depending on which call type you're doing. So this is for updating the cell rate on an order, um, which is neither a position or a swap, right? Um, yeah, and importantly, you don't have to actually transfer tokens to the TRAM extension at all. You just do this within your lock context, and what we do is we update your saved balances, um, and sorry, we update saved balances for the TWAM contract. So the TWAM now has saved tokens, and the person who called lock is the one who has to pay for those tokens.
I see. So it's basically a different approach or design to handling how extensions or hooks are allowed to manipulate deltas and charge users for things or pay users for things. Like in Uniswap, the way they ended up doing it, maybe you know, but I'm just going to reiterate for the audience, is they have like this extra capability uh, called returns delta or like allows delta, and basically that means I think it's in the after hooks, the hook can actually tell the pool manager that, hey, I'm taking this much. I want this much delta. So it like transfers from the till of the caller to the till of the hook, essentially. But here it's done at the forward where you say like instead of specifically separating the tills and then the hook has to explicitly communicate via the pool manager that it needs to get paid for a certain token. The forward is like more like a blank check of saying, I mean, obviously you control who you call, but it's more of a blank check in terms of saying, okay, the plugin can manipulate whatever tills it needs and can potentially do that more efficiently. Because like in the Uniswap example, the hook is only allowed to touch the 2 tokens associated with its pool. And here I assume with the forward, you can touch any token balances,
Yep.
any token deltas that you need, basically.
Yep. I think if you spend a little time, comparing the two, you'll realize that this is much more elegant. Just because there's no like custom functionality or custom code in the core for this. The core handles what it handles, and if you want to do some additional operation or customize logic around a certain operation, you can do that trivially by having a separate operation with forward. And it doesn't add any complexity because you still have to know how to handle that extension in any periphery contracts you write. You have to, for example, you have to know, when you're doing a swap on a MEV capture pool, you have to do forward, and you have to know, what does it return and what does it take instead of calling core.swap. And so that's what this MEV capture router does, is it just has a special case for MEV capture, so you can do swaps on the MEV capture pools.
How does the map capture hook work actually? I'm very interested in this because at Sorella I worked for a long time on our like map capture system. But here the fact that it's just like a simple or seemingly simple extension. Okay, maybe not that simple. I see a few hundred lines, but how does it work exactly? Like how do you measure the MEV to charge traders or arbitrageurs?
Yeah. So my goal with this was that it would be unopinionated, and generally with all extensions, I want to keep it as unopinionated as possible because I want it to be reusable. I want it to be used by other developers or use cases or whatever. But at a high level, like I was mentioning before, you can force people to go through the forward function, and that's what this does. It reverts if you try to call swap uh, uh, just directly on core with the MEV capture extension. And then, so the way it works is when you want to swap on this pool, we look at the tick at the end of the previous block, and however far you move the tick with your swap, you incur additional fees. Um, so uh, like for example, for a sandwicher, what a sandwicher will often do is like even on the USDC USDT pool, they'll see that the price is 1, but they'll see that a trade comes in which sends 10% of the trade through this pool. And so if they want to extract, 2% slippage tolerance, they might move the price of USDC, USDT to like 1.3 or something ridiculous, right? USDC, USDT would never be at a price of 1.3, but they'll move it all the way to that price before the user swaps against the pool. And then right after the user swaps, they'll move the price all the way back down to 1. And so they pay very little fees on this because stablecoin pairs typically charge like trivially low fees. Um, and so even though they're doing millions of dollars of volume on just 2 swaps, maybe they're paying like $4 or $5 in fees. But what they're extracting from the user, because they move the price to 1.3, it could be hundreds of dollars. So this just looks at the tick after the swap, and based on that, it charges some additional fee. So you can see we're loading the tick. We do a regular swap, and then we compute a fee multiplier based on the state of the pool after the tick, and the tick before the swap, or basically at the beginning of the block. So yeah, and then one important thing is that the arbitrager or the sandwich or whatever, they can't. Okay, so this applies both to like sandwiching, and it also applies to arbitrage. Let's say on Binance the price of ETH spikes to $3,100, but the pool is still at 2,900. It might be you don't want to charge the person 2 basis points when they move the price from 29 to 3,100, right? You want to charge them a lot more than that. But it's also in their interest to do that as fast as they can because they're competing for the arbitrage, right? So all of them will, they'll figure out what's the optimal price I can move it to maximize my arbitrage profit. And whoever computes it the best, it's probably some midpoint between 29 and 3,100 per block. But like a lot more of those fees will go to the liquidity providers instead of the arbitrageurs and the miner.
I see. So it's not entirely perfect, or it doesn't attempt to be entirely perfect, but it's like a simple, robust way to at least capture a good chunk of the MEV and somewhat like create like a speed bump for sandwich bots and arbitrageurs to, or like in some cases, at least with the sandwiches, it does seem like this makes it somewhat. This probably makes most of them unprofitable.
Yep.
But yeah, also for normal arbitrage, it takes a decent chunk out. Interesting.
Yeah. So the one way that this is unopinionated, so like people can sort of experiment with it, is how do you determine how much more you should charge them? And we just use the tick spacing. So you can see this fee multiplier looks at how many ticks it moved divided by the concentrated pool tick spacing. So this, by the way, this only works for concentrated pools. It can't work for stable swap pools, which are in some cases full range pools. So you have no way to understand like how much the price moved relative to like how much it should move. So users can sort of play with the parameters here, like the tick spacing and the fee, so that they get max profit, or max capturing of the MEV.
Makes sense.
So I think those are some of like the biggest tricks, or some of the, I'd say, improvements over alternate designs and architectures. I think I'm trying to think what else would be most interesting to go through.
I'm personally also interested in how you represented the pool state and ticks. Like, I'm not sure if you did anything like too crazy there, but yeah, I remember we briefly chatted about that a long time ago.
Yeah. So the pool state, this is probably the biggest optimization between actually the EVM v1 and v2 version. So v1, I spun it out super quick from the Starknet version. And then v2, I focused more on optimization, and this is definitely the biggest one in the contracts. We store the entire pool state, the tick, square root ratio, and liquidity in a single word. So that that's not possible with Uniswap v3 or v4 because square root ratio in v3 and v4 is a 96.64 or 64.96 fixed point number, meaning 64 bits before the radix point and then 96 after. So to get around that, we had to create like a more compact representation of the square root ratio. So our square root ratio is represented differently. We created basically a custom floating point type. So it has two bits which tell you uh, uh, what type it is after those two bits, basically. So if the most significant or 1 1, that means it's a large number. It's a 64.30, and from that you can convert between fixed point and floating point. And so we obviously, because this is running on chain, we have to make this as efficient as possible. So we have these very optimized functions for going to and from square root ratios. And so yeah, it's very hard to uh to get this to be any cheaper than it is, and I think it's like 100 gas to go between the two, um, or at least to go from fixed point to floating point. Actually, it's even cheaper for the other way around. Um, and yeah, it was designed around this optimization, and I think like the hard part is like defining this custom type and then also making all the code safe around it, because you also have rounding when you go between fixed point and floating point, which might make this seem like it's prohibitively difficult to do on chain. Like you couldn't really you could take something off the shelf like ABDK's floating point number, uh, but like you have to be sure that the rounding that you're doing is safe for the user. So that's why we need this like custom representation where we know everywhere that we're going uh, from one to the other, it's like rounding in the correct direction.
Actually, yeah, I was
Um,
going to ask about that next because when you have floating point numbers, you have like these classic problems of precision, where if you have um, a floating point of one magnitude and then a floating point number of a complete other magnitude, is you're going to lose. You're going to kind of maintain the relative precision, where you're going to lose like in absolute terms, you're going to lose like that smaller magnitude value completely. So yeah, I'm curious. I guess it's like mainly just the rounding between modes. So you use like the full precision version to do calculations, and the floating point is just for the storage. Or do you ever
yep.
do math on the floating point representation?
No, we never do math on the floating point. Um, yeah. So that sort of solves our precision issues, because you're not typically trading from one extreme to the other. Like you're not going to be going from a price of you know max the max representable to the 128 over 1 to like 1. You're never going to go that extreme in the prices. But even if you do, uh the rounding only happens when you're storing the result. um yeah. So all the math that you'll see is um still using fixed points. So things like next square root ratio for mat 0, this is still, we take in this smaller type, but it's before we do any math, we always convert to a fixed point. And yeah, we have to be careful to round in the correct direction in every single case. So um, we always round in favor of the protocol.
Yeah, in terms of security, that seems to be like the big headline issue of 2025 and maybe even 2026 is rounding bugs. So very cool to see you, yeah, to see you build something novel, but also like really have the like theory in terms of the rounding seemingly down. And I mean, as long as the rounding error when you convert, because it's not only about the rounding direction, right? I guess it's also about the magnitude of the rounding error when you convert. Like as long as that is also bounded to some kind of magnitude, it's because like you can make the user lose a little bit from rounding, right? But if it's too much, that can also be abused, I guess, by malicious LPs or MEV bots.
Yeah,
So
but I think so it's been a while since I wrote this because this was in the V2. But we the nice thing about smart contract development that today that we didn't have before is tools like Halmos uh, and uh, like formal verification, effectively, essentially. Well, actually, technically, is formal verification. So there's cases where we use formal verification just to make sure our basic assertions are true, and so any test that starts with check, that's actually a formal verification of the code. And we run it in CI, which is amazing. Like, I think for Uniswap v3, we basically didn't do any of that because it was very, very hard to do. And now you have something that works kind of like forge fuzz tests that you can, trivially convert your fuzz test to formal verification and get a lot of confidence in your code.
how does that process work? Do you have to majorly modify anything, or I remember with Halmos back when I was trying to use it, there were some like minor DevX issues with like if you use the Forge STD helper, like it would explode the complexity or whatnot.
Yeah.
Because like the bound
There-
helper under the hood was doing weird things.
There's a lot of cases where it doesn't work. Like, especially if there's a lot of if conditions, like it takes way too long to run, or it just never terminates. But it's extremely useful for our custom floating point type, where we need to check some things like less than or greater than, like just certain operations that we need to know are correct to rely on this type. So I think fuzz tests just aren't sufficient, especially when your assumptions like will rule out the vast majority of inputs. Like there's not that many valid square root ratios in the UNT96 space. Like, I think it's a small fraction of the UNT96 space. Um, so like we need basically Halmos to be able to do this, where we know that less than equals operates correctly on valid square root ratios. Fuzz tests just like wouldn't work.
You also mentioned you used the AI, a lot of AI during the development of Ekubo. Could you go over your setup and why you chose to use it, and like, yeah, what your feel around that is?
Yeah, you can actually see on the contributors graph. You should be able to see this this bot I was using for a while called Mentat. It's basically just like a cloud version of Claude Code or Codex. Nowadays, I mostly use Codex. I use Codex with the latest GPT that's tuned for Codex. In some cases, I would set it to high if it was like a particularly complex refactoring. But there's actually, there's contributions even from Mentat if this thing will load. Yeah, you can see the Mentat bot actually did quite a lot of work for us back in September. Yeah, but this is now shut down, so you can't even use it. You can set up
I
Claude
see.
Code as a GitHub workflow or Codex, and just tag it in issues, or I think it even looks at all issues. But nowadays, I mostly just use local Claude Code or Codex, and yeah, it's extremely helpful because, like I said before, like it's a lot of trial and error to find these optimizations. And so if you can do that trial and error 10 times faster, like that just makes a huge difference in how many optimizations you can actually find and implement. Because normally, you might have higher priorities, and if it takes you, 4 hours to try out an optimization, you're just not going to bother with it. But if I can give it to Codex and come back in 10 minutes and try it out, I can know whether it's worth doing much more quickly.
So did you primarily use LLMs like for the iteration and optimization, just discovering things or searching the space of designs that you typically wouldn't have the chance to search? Or did you also rely on it for like the final implementation, or did you always like hand polish it and like hand write it at the end, and the LLMs were just for discovering what you want to do?
Um, I would say with like smart contracts, you always have to do a pass at the end. Like the LLMs are not that good at writing assembly, um, and like the way typically people write Solidity, it's a lot more defensive. Um, like they're not gonna do these sorts of tricks that we did. Um, so um, so yeah, sometimes like one thing I use LLMs extensively for was when I figured out how much faster or how much more efficient it is to use these custom types for single word stacking structs or whatever. Um, I had to write a lot of these different types, right? And I had to write a lot of tests for them. So I ended up doing it just once, and then I would use Codex or Mentat to basically pattern match what I did for one thing and do it for another type. And a lot of times it would be dead on if I gave it an example. Um, but you still have to check it. You still have to make sure the test coverage is complete, because if it's bugged, obviously, then people can lose money. So it's like, I think of it as like a really, really good autocomplete, because you have to tell it what you want it to do. But yeah, when sometimes if you prompt it just right, it does incredible things.
Interesting. Yeah, I've also recently started playing around with using AI a little bit for smart contract development, and at least for drafting and like sketching out things, it does add a certain amount of speed, but I don't know. I cannot get it to reliably do things nicely. But just for like sketching out or like broad strokes, um, it's pretty good.
Yeah. So like an example where it just like sped things up massively was I came up with this idea of a boosted fees extension just last week, or yeah, about a week and a half ago. And I had Codex write the first draft. And it had a lot of issues. Like it basically just wasn't correct. But the amount of typing that it saved me was massive. It like I only had to fix the parts that were just incorrect. So yeah, I mean, there's so much scaffolding, right? Like this is one contract that's related to boosted fees, but we also have to write a data fetcher for it, which is sort of pattern matching on this other data fetcher, and that's like another 100 lines of code that I don't have to write. And
But what do you need a data fetcher specifically for the extension? Doesn't that state live separately anyway?
yeah, so because we don't have any getters, we don't use getters basically at all. So we just use exposed storage on everything. Um,
I see, even on extensions. So this is mainly just to make the dispatcher smaller and more efficient.
yep.
I see.
Yeah. Um, so yeah, everything, unless the getter can be much more efficient because it's written within the contract, I try just to use exposed storage, because it's more future proof. You don't have to think of all the ways that people want to fetch the data from your contract. You can just have this one function, and then they can do it in just a single call to get all the data.
Actually, inspired by the exposed storage pattern, I rediscovered this thing that, I mean, somebody else on Twitter told me that somebody had already done it. This way of doing exposed storage, it gives you like the same flexibility of exposed storage, but also the ability to do like quasi like on par in terms of gas efficiency if you need to do more complex things, which is your exposed storage handler. Instead of like taking a list of slots or whatever, it just takes an address and an arbitrary bytes payload, and then delegate calls to it, and then whatever it returns, it reverts and bubbles up that data. So it can still access all the storage however it wants to. It could be a Huff contract, or it could just be a plain old Solidity contract, like however efficient you want it. And then it's
Yeah.
also down to just like one single method in your main contract instead of having like one single. At least in V4, I think they had like 4 different function variants. They had like an external T load, external S load, external S load
Yeah.
with a list, external T load with a list. So like
Mhm.
it's all down to one, and you get like the full power. So I thought it was also an interesting pattern that I'm going to explore in my code bases, but could be interesting for something like this as well, I guess.
No, I mean that's very smart. I hadn't thought of that. I think that would solve my problem where, in core Oracle I have these custom getters just because they're more efficient. Um yeah, that's a very good idea. I think delegate calls a little bit scary, but obviously you're reverting, so um actually I don't know, can you not like do an early return in the delegate call would return, not the
Yeah.
um yeah. Yeah, it makes sense. It's a very good idea. I hate to have regrets about something I just deployed a month ago, but at least that one's not too big.
That's always the notion of the space, and that's why I actually really appreciate you hopping on this, and why I wanted to do this is because it like puts the knowledge out there for others, and I don't know, I personally learned a lot from this, and I think others can benefit as well to like make the future contracts better, both in security and in gas actually. One thing for my personal interest is like you have a very novel style in terms of like how you develop Solidity, both in V4 and here. I've noticed that like with the custom types and the exposed storage and the till pattern, like where do you get these ideas? Is it just like from iterating, or is it like your experience? Where do you get these ideas from?
Yeah, so the till pattern, um, that was kind of just me looking at uh like what is the most expensive part of swapping on Uniswap. Um, it's probably just the sheer number of token transfers. Like, what if you could keep them all the tokens in the same contract? Um, well, sure, you can do that, but you might need to like give this one contract like a list of swaps. But then, hey, what if you want to do swaps and position updates? Um, uh, well, that you basically have to create a virtual machine, a VM within your core contract, which lets you uh, specify, hey, do this thing, put those things onto the stack, pass them to the next thing. Uh, but that felt kind of crazy to me to do because the EVM is already a virtual machine, and I don't want to define my own VM within the EVM. So I was thinking, okay, well, what if I just gave them a callback? And then I kept track of these things that they did in the callback. So that was kind of that's how I got to the idea of the till pattern. But then, the problem with that is that you're replacing these token transfers with all these S stores and S loads. But like, at the beginning and the end of every call, those values are going to be 0 because they're just transient, right? So that led to the transient storage EIP, and that's why I went down that path with trying to get that included to Ethereum.
Oh, interesting. Is
Um,
that where the EIP comes from as well?
yep, yep. And it's
Wow.
funny because
Okay.
there was a lot of controversy about it coming from Uniswap. People were like, "Oh, Uniswap's trying to get like a monopoly on the Ethereum by introducing this opcode, or like this is gonna create so many smart contract vulnerabilities because people won't clear the state at the end of the call." It was crazy. It was extremely political for absolutely no reason. But and I couldn't be open about why I wanted this EIP because V4 was still in development. So um, yeah, it was a fun time, but it was also very stressful arguing about something that was just obviously good for the EVM.
Yeah.
Um,
So I think a lot of the controversy stemmed from this like completely false article from Adam. I forget his second name, Adam Cochran or something. Like he used to be really big on crypto Twitter. Um,
Yeah,
but yeah, I remember also being outraged by it. Like that was insane that it got delayed an entire hard fork because of that. But
yeah,
oh well, that's a
yeah,
nice history nugget for the people who are newer to the space.
yeah. So yeah, I mean, I think like the easiest way to come up with these optimization ideas is just to do like profiling, look at what's expensive, and if you when you get used to like the EVM, there's some things that are gonna be like, what the hell? Why does that cost 4,000 gas? Why does that cost like 8,000 gas? And then unfortunately, a lot of the times it'll be like, oh, because Solidity is adding all this other stuff. How can I avoid it from? How can I avoid the extra stuff that Solidity is doing? I mean, there's cases where Solidity will add S loads for like the same uh, storage slot, like multiple S loads, just because you're reading two different values from a struct. So, uh, yeah, it's definitely a lot of times just working around the Solidity compiler. Um, but yeah, you always start with profiling. Like any performance optimization has to be sort of guided by that.
As a dev tooling slash compiler dev myself, what is one if you could choose one feature in the Solidity language or like in the smart contract tooling arsenal that would have helped you with V3 and beyond, like what would it be? Like, what would be the one feature or tool that would like be really useful to you?
Yeah, I think. I mean, I think it doesn't even really exist yet, or maybe I haven't figured out how to use it right. But the like being able to step through Solidity code and see for each block like how much gas that takes, like for a particular test, for example. I think there's like forage debug, or maybe it's cast debug, but I think it runs at like the EVM debugger level, not like at the Solidity level. So being able to step through your code and seeing how much like each block took in terms of gas would be massive. Or even if you had like IDE integration where I could see this block costs X amount of gas in a test, that'd be absolutely wild. Um,
Yeah, I mean there
yeah,
is the like if you look at the Foundry call trace, you can kind of see gas in terms of like top level calls, like EVM calls. And then I think they do have like a decode internal flag or something that works so in terms of internal calls. I'm not sure if you tried that or how reliable that is.
never
Um,
tried it.
but yeah, the debugger, yeah, it just steps through the actual instructions, and then sometimes it like works 30% of the time. You see like the actual mapping on the side, but it's not very nice. There's also a since a while I use that occasionally. It's pretty cool actually. It's there's a flame dash flame chart when you run tests.
Yeah, I use that a lot. That's what I mean by profiling. Um, yeah, I love the flame chart and the flame graph. It was crucial to like development. Um, so
Cool.
yeah,
All right. I mean, there's so much more we could dive into, but I think this might also be a good point to stop. Yeah, thanks for coming on and sharing some of the smart contract dev alpha. And yeah, excited to see what you build with V3 on top of V3 or maybe even V4. Maybe you discover more optimization opportunities. And yeah, let's see.
yeah. I hope not. I mean, I spent so much time on this, but yeah. Thanks for having me.
Of course, anytime. All right. Bye, everyone.